In our last lesson, we looked at limits from a graphical perspective, and in this lesson, we'll take an algebraic approach to limits. So our learning target is that we will calculate limits using algebra. And this gives us a great chance to practice those algebraic skills that'll be important throughout the course. When we're given an algebraic limit, the first thing we want to think about is what would happen if I substituted in the given c value. If I come up with a limit value that's undefined, perhaps I need to take a series of short steps, algebraic steps, that would lead me to a better answer. And those short steps are to factor, simplify, and then resubstitute the original c value to see if I get a different result. Let's illustrate that process with the first example. Our limit is as x is approaching 1, so that 1 is the c value mentioned. So we're going to think about substituting that 1 for every x that we see in the algebraic expression. And in the numerator, I would get 1 plus 5 minus 6, which is 0, over 1 minus 1, which is also 0. And you may not have encountered this value before, but 0 over 0 is actually not a value at all. It's called an indeterminate form. And we'll talk about it later in calculus when we get to something called L'Hopital's rule. But that's something to look forward to. For today, we just have to use our good old algebra skills to get us to a better answer. As we start to work this problem out, it's important to remember that we need to carry our limit statement with us through every step. And that's easy to forget, so try to train yourself to start with that. And then we jump into our factoring. So the trinomial factors nicely on the top to x plus 6 times x minus 1, and the difference of squares on the bottom is x plus 1, x minus 1. So once we've done our factoring step, the object is to get something to simplify so that when we try our limit again, we'll get a better result. So we see that the x minus 1s will cancel, and then we'll resubstitute our x value from there. Once we cancel our x minus 1 factors, the limit expression becomes x plus 6 over x plus 1. Substituting in the 1 for the x values, you end up with a final answer of 7 over 2, which is a much better answer than 0 over 0. And just to point out, the right time to drop the limit notation or to stop using it is when you do substitute that 1 in for the x value. As we look at the second example, I'm going to do a quick mental check by substituting 0 in for x for my numerator and denominator. I quickly find out that it's going to give me that 0 over 0 indeterminate form, so I know I'm going to need to do some algebra. It is going to be another factoring problem, but not the nice trinomial or difference of squares factoring we saw in that first example. This one, if you look at the numerator and denominator separately, you'll notice that they each have a greatest common factor, so we'll use a GCF. By coincidence, they both happen to have a GCF of x in the numerator and denominator. That's not always the case, but it works out nicely for us because after we factor out that x, we can cancel the x on the top and bottom and then proceed to reevaluate our limit. So with the GCFs canceled, the limit statement becomes 3x plus 1 over 5x cubed minus 6. I'm going to go ahead and substitute in the 0, meanwhile dropping the limit notation that I no longer need and come up with a final answer. Substituting in the 0 canceled out a couple of the terms, and the final answer is 1 over negative 6. The next two examples are different in that we won't be factoring, but they're still algebraic limits because they are going to invoke either a property of exponents or maybe a property of a function that we're expected to know for the AP exam. So let's take a look at both of those. In the first example, when I substitute the 0 for x in my denominator, I get 1 over e to the 0. So that's prompting us to recall a property of exponents, that any base to the exponent of 0 is 1. So that's going to give me a value of 1 over 1, which of course gives me a final answer of 1. In the next example, when we substitute the 1 in for x, we come up with a natural logarithm of 1, and that is a value we're expected to know without a calculator. So if you're a visual person like me, it helps to remember what that natural log function looks like and to know that it actually has an x-intercept at x equals 1. So our numerator will be 0 over 1 squared, will be 0 over 1, which is 0. And I want to point out that that answer of 0 is different than when we got the indeterminate form in the first couple examples. 0 over 0 did not equal 0, but 0 over a number equals 0. So let me just refresh your memory on the difference between the two 0 answers. So here's a little sidebar here, and I actually said that there were 2 scenarios, but there are 3. If you have a 0 on top of a number, let's just call it k, that's okay, so that equals 0. If you have a 0 in the denominator under a number, let's call it n, that is not okay, so we call that no, and that is undefined. And what we saw earlier today was the 0 over 0, and that's called indeterminate. So there's actually 3 scenarios here that you need to be comfortable with. So just one last comment on that example. You do need to memorize that the natural log of 1 is 0, so you might just want to make a note to yourself too. The next 2 examples involve algebraic procedures that are quite complicated, so I think they would be best to work out together in class. It uses something called a conjugate and LCD. So let's get down to the section on piecewise functions. When we start talking about piecewise functions algebraically, it's going to allow us to make a nice connection to the graphical perspective that we talked about in our last lesson. So you might remember me drawing this generic picture of a function's left and right pieces meeting up at a y value, and the point may or may not be there. It does not have to exist for the limit to exist. The point of this picture, or the bottom line, is that you need to have the left and right piece or limits be equal. And so we're going to take that visual representation and look at it from an algebraic perspective. The first thing we need to do with a piecewise function is determine which is the left and the right piece of the function, and where does the point exist as well. And that's determined by the inequality that you're given for each piece. So if x is less than 3, that's going to be on the left side of 3. Greater than 3 is on the right side, and the point exists wherever the equal sign is. So I tried to circle and put an arrow there, but it got a little messy. We're going to start by writing down left equals right, because that's what we want to test. That's a hypothesis. But L equals R is not a mathematical communication of what we're doing. So we're going to need to, in our next train of thought, come up with the limit notation that expresses that thought. So all I have so far is the limit notation as x is approaching 3, and I knew the x value was 3 because that's where the 2 pieces of the piecewise meet up, and I've expressed my left and right limit using that superscript of minus and plus. And notice I left a space to write the function in. You could write f of x both here and here, but then on the next line you'd have to write the actual function description for each line. So let's go ahead and put those here. So we decided at the beginning of the problem that the left piece of the function was represented by 6x minus 4, the right piece by x squared. So now that I have communicated my hypothesis that I'm testing, the left and the right limits, I'm going to go ahead and substitute the 3 into both of those pieces of the function and see what happens. When I substituted the 3's for the x's, I came up with a mathematical statement that is not true. 14 does not equal 9. So we have found out that our hypothesis was not true, the original hypothesis. And I was using that word on purpose to show you that we didn't know what was going to happen until we actually solved it out. So we'd have to go back and slash through those equal signs, and then we have to communicate in a conclusion that the limit, the left and right limits are not equal, and therefore the limit does not exist. So it's a very short statement to write, but it's got a lot of mathematical notation, and it's something you might have to get more comfortable with as we go on. You may or may not have seen this symbol before, the 3 triangular dots. That represents the word therefore, so that starts a nice conclusion statement. Our limit of our function f of x as x approaches 3 does not exist, and we don't have to further explain that because we have proven that we tested the left and the right limits and they were not equal. So that is our justification. So this is an example when we found a hypothesis that was not true. This example is actually going to work out that the limit does exist, but I'd like to save this example to work out in class to see if you have any questions, and then we'll finish up these notes with the properties of limits. I'd like you to take a couple minutes and just look at each property, its name, and the example here that represents the property, and just see if you can identify what's going on in each property. Then we'll talk about them in class when we get together and work out the examples below.